So today what we're going to do, we're going to study area between two curves. And what we've learned in the past is that when we want to find the area between the x-axis in some kind of curve, we can look at little rectangles and take the curve and that will find it. If it's below the axis, then I can just, if I want to find the enclosed area, then I can just do the absolute value of that scenario. But when we have two curves, there's not a lot of difference. We have to recognize that when we're looking for the area, we're actually we're taking up all these little rectangles with this distance here times this height. So the height of all these little rectangles. And so the distance is dx, but the height here is going to be the top function minus the bottom. So the area there would be whatever f of x is minus g of x. That's the height, and then the distance here is dx, and we add up all the rectangles. But if the curves start to switch around, and sometimes we don't always know which one is g of x and which one is f of x, one of the things we can do to ensure that this height is always a positive value, we can go in here and put the absolute value on. So if we want to find the area between f and g, we take the derivative from some value a to b of the absolute value of f of x minus g of x dx. If we know definitely which one's f and which one's g, we don't actually have to put the absolute value on, but if we are unsure or if it switches throughout the integral, putting the absolute value on will ensure that it always calculates out correctly. And since we have a calculator to do it, we will utilize it. If we don't have a calculator, we have to switch it back and forth. Well, let's try an actual example to see what this actually looks like in real life. So given these two functions, sine f and g, sketch the functions, find the point of intersection. So I'm going to go to my calculator. I've already put them in. Check my mode is in radians because calculus is always done in radians. And I'm going to zoom. I'm going to zoom to decimal zoom, which just means it goes from like -5 to 5 and 4 to 4. It's just zoomed in more so. And so I'm looking for, here is the two scenarios, and if I pull out a graph here, that's a little bit easier to look at and see. We need to find the points of intersection. Well, I know this here is 0, 0. I'm going to find this one and this one here. Okay, and so to find, I'm going to go second trace, I'm going to find the intersection. My first curve, my second curve, I'm going to put it close to the -1 value. And so here is my intersection. I know I need, so this is -1.31716. And what I'm going to do, because it's in x already, if I come to my main screen and if I look at x, it holds on to that value until I move the cursor again. So I want to keep it. I'm going to store that in alpha a. Okay, and so now a is whatever that x value is. When I go back to my graph and I'm going to find the other intersection point, which I'm pretty sure is going to be the positive value because it's symmetric, it is indeed the positive value. So this is a positive 1.31716, comma, -0.968. It's asking for the points intersection, so I need x and y, and this is going to be the positive 0.968. Okay, so I'm going to take this now and I'm going to store that into b. So let me quit this. I'm going to look for the x value, and I'm going to store that into b. And so now this is a, and this is b. And now I want to find the area between the two. So I'm looking for all of this area in here. There are several ways for me to do this, and I'll outline them all. Okay, one of the ways that I can do it is I can just simply go, if I want to find the area from -1.317 to positive 1.317, I take my upper curve minus my lower curve, but because it switches, I can just do the absolute value of the upper curve, which is the blue curve, which is g of x, which is x cubed minus x, subtract sine of x, d of x. If I throw this in my calculator, it'll work. I could have also written, because f and g are defined up top, I could have just simply have said g of x minus f of x. And because they're defined for me, this is sufficient as well. So if I look at my calculator, I know that this here is actually y1 and this is y2, just so I can keep track of what my variables are. And if I quit here, if I want to do it in my calculator I just simply go to math, number 9. I'm going to go from alpha A to alpha B, and I'm going to go the absolute value. So I can go alpha window, which is my absolute value. I could have also gone math to number and done absolute value. That works as well. But so now I'm in here and I want to say y2 minus y1. So I'm going to go alpha trace y2 minus alpha trace y1, and it's going to be dx. And that will give me the area to 3 significant figures, 1.73. Now, there's other ways I could have done this problem. Because I have the absolute value in here, I could have just as easily have switched these around and said f of x minus g of x, because this part region here has that. Another way I could have done it is I could have went, because of symmetry, these two parts are the same. I could have went 2 and gone from 0 to 1.317 and did the red curve sine, which is f of x, minus the bottom curve d of x. And I wouldn't need the absolute value because it doesn't change, and I chose the sine x to be on top. That would also work. I could have also, without the absolute value, I could have went from negative 1.317 to 0 of the blue curve, which is g of x, minus the bottom curve, the red curve. And I could have then added it to 0 to 1.317 and done f of x minus g of x dx. And then it would just, because it would be the upper curve, the sine curve, minus the cubic curve. And so there's lots of different ways to do this, but if you have a calculator, for sure the easiest way is to just find your limits, put in absolute value, and then just crunch it up.